Hello everyone! Once again, it's time to get into mathematical logic. And so far, stream bitrate is up and stable. Well, stable-ish, good enough. Everything seems to be running, unlike Thursday, in which the upload bitrate was at 90 kilobips. Completely unfeasible. Okay, things look good. So, we march on. We keep going through our little course of introductory mathematical logic. And today we start with our twin method for studying mathematical logic. So far we have studied, or we have approached this problem, this language, this formal, made-up, highly abstract language, through assigning arbitrary values, one of which we have called the designated value, which we can call true or one or on, or however you prefer, and the other one, which is the non-designated value, which we can call false, off, zero, and so on. And we have studied the main problem of mathematical logic, that is to provide very formal model of what is logical consequence by defining this language, by defining a set of rules of how the multiple symbols can be interpreted. And when we say interpretation here, we don't mean like an actual linguistic interpretation. We just mean a truth function or a value function, if now that we have gone a little more abstract than true or false. We have stated that we have propositional letters, which can be either true or false, and that gives us a combinatory matrix. The more letters we have, the more combinations there are, in which case one is false and the other is true, and vice versa, both are true, both are false, and it keeps adding them on the more letters we have. And we also have symbols for the logical connectives, which we have called conjunction, disjunction, implication, biconditional, and negation. The negation basically inverts the values of whatever formula it is connected to. The conjunction is only true when both parts it is connecting are true. The disjunction is true when at least one of the parts is true. The implication, we can understand it as the truth of the first element guarantees the truth of the second element, and so it only brings out false if the first element is true and the second one is false. Or we can also see it as a less or equal than, so that if we see it as ones and zeros, the only combination in which it brings out zero or false is when we say that one is less or equal to zero, which is not the case. And then we have the biconditional, which is true as long as both parts have the same value. It's also called the material equivalence symbol. Now, that is well and good. But there are certain problems with this method. One, it restricts itself to a certain arbitrary interpretation or value assignment. And some people may have some philosophical problems with that. For example, people who don't agree that everything is either true or false. Maybe they don't want this machinery for... Maybe they don't want that kind of implication that comes from classical mathematics. In classical mathematics, formula are either true or false within a system. And maybe some people don't want that. Maybe some people think that that is too restrictive on reasoning. Or maybe some people don't like the idea of how computationally limiting combinatory matrices can be. That, however, is a bit of an anachronism, because the people who did this, the people who built these systems of mathematical logic, they eventually built computers. Like, so far I've used a lot of computational comparisons and metaphors, and they work because what we now call computers was a byproduct of the work these people made. So of course it's gonna fit what we now experience through personal computers. But that is more of a pedagogic approach. I mean, I make those comparisons to make it easier for you listeners to approach and understand these problems. But if I were to be more philosophically and historically rigorous, I will have to say what I said just now, that computers are a product of this effort for creating a mathematical logic. So historically, what was it that some people didn't like about the semantic method, or the truth, or the value assignment method? One of the purposes of all this, why this all was invented, was because the ideal was at one point something that philosopher called Gottfried Wilhelm Leibniz conceived of turning discussions or debates into a calculation problem. Something that you could just input into an impartial machine, and by applying a series of completely impartial, formal, and abstract processes, the machine will just crank out the result and will give a supposedly objective answer to what the debate or discussion was. Some people thought that was a great idea. And I'll be honest, at one point in my life, I thought so too. The idea of removing all of the confusing parts, all of the parts that can be misgiven to malicious interpretation, and just having a perfect process that will unerringly give us the correct result, that is tempting. Or at least it was tempting at one point in my life before my general philosophical outlook changed to the point where that just feels ridiculous. But for many of the people involved in this project, the project of mathematical logic, that would have been really cool. At least in mathematics. The idea that a properly presented mathematical project could just be reduced into a process where you just apply rules and ordinarily get the result, that would be great. I mean, it works for a lot of simple mathematics, what we now call algorithms. I mean, I say what we now call algorithms, as we haven't been calling them algorithms for literally hundreds of years. But yeah, basically the idea was, what if we could take an actually difficult problem, a problem about mathematics or philosophy, and feed it into an algorithm and have the algorithm give us the correct result? Imagine if we could do that for everything. No more discussions, no more confusion, no more arguing pedantically about every single bit, just perfect rules, perfect results, bam! And that is the kind of goal or idea that this other camp of mathematical logic, which we will now call the syntactic camp, wanted. And we will see if they got that, if they achieved their goal. Hello, Rupert. Rupert says, got right in time after the last essay of the semester to be rewarded with devilish homework solving. Yes, we are now going to solve the homework. Do you have a solution for the devilish puzzle? SA stream helped a great deal. Great, that's great to hear. I'm really glad that helped. Okay, for those who weren't here last week, or those who didn't see the homework over at my Blue Sky, I'm gonna read out loud the... Oh, Rupert wasn't able to... Okay, we'll work through it. Like, I'm not just gonna give the answer, I'm gonna give the general method for reaching the puzzle. Okay, so the homework was this. A certain country is inhabited only by truth-tellers, that is, people who always tell the truth, and liars, people who always lie. We know from earlier streams that the format of these riddles are the islands of knights and knaves, where knights are truth-tellers and knaves are liars. The problem with this is that I like Smulian's definition better. Knaves aren't liars. Knaves are people who always tell falsehoods. Lying and telling a falsehood is not the same thing. But we'll go with that when we cover the Pinochet paradox. Moreover, the inhabitants will respond only to yes or no questions. So no open question, just questions that can be answered with yes, no, and that's it. A tourist comes to a fork in a road where one branch leads to the capital and the other does not. There is no sign indicating which branch to take, but there is a native standing at the fork. What yes or no question should the tourist ask in order to determine which branch to take? So implicit in the exercise is the fact that you can only ask one question. You can only ask one question, and again implicit but not clear enough. You do not know whether the native is a knight or a knave. So you only get one shot. And you have to engineer a question that can be answered only with yes or no, such that no matter which type of person is answering, they will give you enough information to know which of the branches is the correct one. The correct one being the one that leads to the capital. Hints. Let A or any other propositional letter stand for you are a truth teller. And let B stand for the left-hand branch leads to the capital. Whether it's left or right, it's relevant. It's just select one of the two. Construct by means of a suitable truth table a statement form involving A and B, such that the native's answer to the question as to whether this statement form is true will be yes when and only when B is true. Now, the book gives us a lot of hints, especially in this bit. When and only when. Oops, too tiny. So Rupert, what logical connective reminds you of when and only when? If and only if, right? Yep, the biconditional. So we want to find something that says yes if and only if B is true. That way, if B is false, we get a no. So that is how the answer is going to look like. We're going to ask a question such that if the person says yes, then the correct road is the left one. And if the answer is no, the correct road is the right one. Because we know that if B is false, basically if not left, then right. The problem comes when we don't know if the person is a knight or a knave, a truth teller or a false sayer. If we knew that the person in front of us was a truth teller, we would just ask, hey, is the road that leads to the capital the left one? And they would just say yes or no. If they say yes, then left. If no, then right. As simple as that. But if we ask that question to a knave, they will say the opposite. And we don't want that. But we're not asking B by itself. We want something that inverts as well. Because if a truth teller is asked B, then no problem. But if a false teller is asked B, they will say the opposite. They will say true when false and false when true. But hey, what if we could just integrate this idea of inversion? Like that, such that so when a truth teller is asked if something is true, they say the same. But what if we inverted this somehow, such that the answers will be the same? Now, of all the connectives that we have, which one gives us true when true and true. How do I put it without spoiling it? Let's see by process by elimination. A conjunction will not work because that will just that only works in the first case. If we're asking a truth teller and the road is the left one. A disjunction will not work because it is two legs. As long as one of the elements is the case, whether we are asking a truth teller or whether the question is correct, we'll get a true. And we'll still get an inversion if we ask an ape. The material conditional is basically a disjunction as well, with the negation in the first part, so that is too vague. So the answer, the only connective that has this switch or deals with the switch when asking an ape, but also is yes when and only when B is true, is not surprising at this point. The big conditional. Let's go through the possible cases. So the question we should ask is, are you a truth teller if and only if the road to the capital is the left one? If we're asking a truth teller and the road is to the left, they will say yes. If we're asking a truth teller and the road is to the right, they will say no. The inversion comes here. Oops. The inversion comes from the fact that liars will automatically invert. Or rather, knaves. If we ask an ape, are you a knight if and only if the road to the capital is to the left? This statement will be false. So they have to say the opposite, and they have to say yes. Are you a knight if and only if the road is to the left and the road is not to the left? Then both sides will be false, and they have to say the opposite. So they will say no. So if we ask this, then we don't know the identity of the person saying it, but they both will say the same thing. And they will both tell yes when the road is to the left, and they will both say no when the road is to the right. And that is the first devilish puzzle. So next time you face a knight and knaves puzzle in a game or a role-playing tabletop experience, be mindful of this, and you may impress everyone at the table. Okay, but while that's a good puzzle, a good brain workout, that's not what we're going to work here today. We are going to start dealing with we have the truth teller out of the pocket. Yep. So we want to explore this idea of what if we could just feed an argument into a perfect algorithmic machine that will tell us through a finite number of rules whether the argument is valid or not? Before we deal with the problem, the philosophical problem proper, let me present to you the rules of the game. We are going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 rules. One for each logical symbol, whether it be negation, disjunction, conjunction, implication, or be conditional, and this one. These two are special because these two deal with a symbol that we haven't really treated like a logical connective before, but that is what in Spanish is here is named here constante falsedad, which shouldn't be difficult to understand as constant falsehood or contradiction, which again philosophically I have to declare that not everyone thinks that constant falsehood and contradictions are the same thing. In classical logic, they kind of collapse. They kind of collapse into the same thing, but there are other systems and definitely other philosophical conceptualizations of what a contradiction is. In classical logic, a contradiction is also kind of collapse into an impossibility. Again, this is because when we're dealing with the highly abstract, unchanging world of mathematics, contradictions are undesirable. And they basically work as error states. So let's start with something funny about this. The rules come in pairs. Some rules are for introducing a symbol, and the other rules are, well, they are called elimination rules, but that has proven to be a bit confusing because we're not actually eliminating anything. It's more like we're breaking down the symbols or like analyzing them. They were just called introduction and elimination because of the people who made this up. They wanted like a pair, and I mean the introduction rules do introduce, so that's clear. But the elimination rules, I mean, they are eliminating in a way, but not. When we talk about elimination in this context, we're not saying that we are going to erase what we have or that it is no longer accessible. More like we're just eliminating one layer of complexity, if that's how you want to mentalize it. Or you can just abstract it and say, okay, these are the I rules and these are the E rules, and that's it. So what we're going to do, we're going to produce a chain of symbols. Every step in our chain is going to be a well-formed formula of our language. And every step is going to be justified by one of these 12 rules and a special declaration, which is not a rule, but a special declaration we call premises. So every step in our chain of symbols has to be justified by either being a premise or by being a transformation. Justified by one of our 12 rules. And that is it. The end of any chain in this process, we're going to call conclusion. And the chains can extend an arbitrary amount, but they are always finite. So for example, when you see M or N or O like this, these are not letters, those are variables for not the number of the step that we're in. So this M can be 2, which will mean that this will be 3 and this will be 4. Or, theoretically, if necessary, this will be step 836, 837, 838. And to the side, we see this. We see this. Does a concatenation of steps count as a layer or element lost? No. We will deal with the layers soon. Don't worry about it. A concatenation is just a set, an ordered set that goes 1 plus 1 plus 1 plus 1 plus 1. So a concatenation is just a sequence that has an extra bit added, and the extra bit is always added one step at a time. That's what I mean by concatenation. So to the side of the chain formulas, of the well-formed formulas, we will see this nomenclature. We will see a dash, then an I or an E, then a symbol. In this case, it's the constant falsehood or contradiction. And then we'll see references to the adequate steps. Which steps are adequate depends on the rule. When they are separated by a comma, that means they are individual steps. That means step M and step N. And when they are separated by a horizontal line, that means we're referencing a sequence of steps. Basically, from step N to step O. So, separated by commas, individual parts, separated by horizontal lines, the sequence. The sequence that starts with this number and ends with this other number. Okay, let me go over some of the rules and I'll provide an example so this becomes a little more clear. So this is a rule of conjunction introduction. Please, English speakers, introducción in Spanish means introduction. Eliminación in Spanish means elimination. They come from the same Latin root. It shouldn't be too difficult to translate. Conjunción means conjunction. Condicional means conditional. Disyunción means disjunction, and so on. It's not... It shouldn't be too difficult. Okay, so what does the rule of introduction, conjunction introduction tells us? If we have any two well-formed formulas, and I think, okay, if it wasn't clear enough, here alpha and beta are variables for, regularized rule. That is the most confusing part, but I think that one was obvious. So alpha and beta are variables for any well-formed formula of our language. Remember that a well-formed formula for language is anything that is a propositional letter, or anything that is a well-formed formula plus a negation, or any two well-formed formulas with a symbol, whether it is conjunction, disjunction, condition, biconditional, and so on. So basically this rule tells us, if any two formulas are in the proof, then we can build the formula, the first formula and the second formula. That's it. Intuitively, this makes sense. If we have proven that A and we have proven that B, then we have also proven that A and B. As a final note, this rule is commutative. That means that it is equally valid to construct this formula as it is to construct this formula. Instead of saying M and N, we will have said N, comma, M. The order does not matter in the conjunction introduction. Okay, and the rule of conjunction elimination is also very simple. If we have proven that A and B, well, that means that I can extract A or I could extract B from A and B. If two things are true, thanks for the hydrate. If two things are true, then I should be able to say, okay, the first one or the second one. I can extract whichever part I want. I can extract the first one, I can extract the second one, and if I want to, I can extract first the first one and then the second one, and that's it. Okay, let me do a brief proof of this. So it's not as abstract. Or as vague, rather, because everything is abstract now. There we go. No, wait, this is not a premise, this is a conclusion. So these funny symbols mean that this is a desired conclusion. Basically, this means when you reach this sequence of symbols, you can stop. And this proof is going to be very simple because in step 2, oops, I can just say, hey. In fact, I can literally just copy and paste. And say, hey, this. Why? Because I can do the elimination of the conjunction situated at 1. And that's it. The proof is done. I have, through a series of justified formulas, achieved the formula that I want or was input to do in only one step. I mean, it's not very satisfying that humanly speaking, that I reach it in only one step, but it's valid. It counts as a proof. In fact, one of the more asshole-ish exercises I gave to my students was the following proof, the trivial proof. From the premise P, conclude P. Okay, done. That justifies my definition of logical consequence using syntactic methods. Every formula is justified by either being a premise or by being a transformation of using my rules. And I arrive at the conclusion. That's it. I don't need to do anything. P is a proof of P. This, in an argumentative context, is a fallacy. It's called begging the question. It's like, okay, how are you going to prove that something? Oh, well, if I assume it's true, then it's true. I mean, technically, yes. But is it true, though? Oh, I don't know. All I know is that if it were true, it will be true. Yeah, that is undeniably the case. That is technically true. It's also completely useless, but it's true. So yeah, I used to troll my students a lot with this one because they were like, but how? How do I? What do I do? You do nothing. You have arrived at the proof. It's technically true. Yeah, but that's not how real humans argue. I know. But it's how the definition of logical consequence works. And that's it. We're done. Okay, so now that we have some examples, let's go over all of the rules so we can have like some actual exercises going on. Conditional introduction is weird because we have to use something called a soft proof. Let me type in the chat. So, soft proof. We can construct or introduce a conditional if we build a secondary proof inside the main proof that starts with the antecedent and ends with the consequent. Because why? What is the conditional telling? Oh, if the first part were true, then the second part is true. And what are we doing here? We're doing a smaller proof when we start with the first part, the antecedent, as a hypothesis, and then through other rules, we reach the consequent. So that means that if the first part were true, then the consequent will also be true. Conditional. That's why it's called the material conditional. So we start a smaller proof inside our main proof. We can use the material and the formula from the main proof in our pocket proof, but very important. Any of the material that appears here, it cannot come out to the main proof, because all of this information is contingent on the hypothesis. One of the main cliches that I hate about Ben Shapiro and Charlie Kirk and similar entities is that they violate this rule all the time. They start with these insane, arbitrary hypotheticals, and they just go, well, let's assume, for the sake of argument, and blah, 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 blah. And then they try to extract something from that hypothesis into their main argument, and you just go, okay, but we're just assuming. None of what you said has actual material merit, because I just conceded the hypothetical to see where it goes. But then you're extracting material from the hypothetical into the real, and that is completely invalid. That is not okay. The only information that we can extract from this is this condition. If the first part were true, then the second part will also be true. But if later in my proof I try to justify one of the using any of the other rules, and I use, for example, n, so basically this, that's wrong. Don't do that. On the other hand, the conditional elimination is one of the most elegant, valuable, fundamental processes for all of mathematical logic. This, the medieval scholastics called modus ponendo ponens, or modus ponens for short, which basically means mode of affirming by affirmation. And I think it's the most representative rule of this entire exercise. If the first thing is true, then the second one is true. Hey, guess that? I got the first thing. Oh, well, then, if I have a conditional and I have the antecedent, then I can affirm the consequent. So if the antecedent is affirmed, the consequent is affirmed. That's why it's called mode of affirming by affirmation, modus ponendo ponens. The meme version of this was achieved in SpongeBob when Evil Manta tried to explain to Patrick that he owns a wallet. He provides a series of proofs, such as, okay, if your photo is in the wallet, then you must own the wallet. Patrick says, yeah, that's reasonable, I agree. Well, your ID is in the wallet. That means that this must be your wallet. And Patrick says, no, I don't think so. So that scene is very illustrative of kind of what it means to make an inference. If you have this information, then you also have this information. In more formal abstract settings, that means that if I have a conditional and I have the formula, I can extract the second formula or the consequent by this rule. The rule of disjunction introduction, you say introduction, I guess I did. Disjunction introduction is very simple. If I know that a disjunction is true when at least one of the parts is true. So if you have a formula, then I can just say, well, I mean, today I will eat tacos. So it's also true, or I can just say that, okay, today I will eat tacos or pizza. I mean, yeah. In fact, I am losing information. I'm losing specificity when I do this. Because I know if I am eating tacos, then I am eating either tacos or pizza. But if I am eating tacos or pizza, then I cannot know specifically that I am eating tacos. So it's a one-way rule. Also, this rule is commutative. So I can add the first part or the second part. It doesn't matter. Now, the rule of disjunction elimination is a lot more complex than its introduction one. So what we do is, if we have a disjunction, then we will build two subproofs. And we will basically say, okay, look, I don't know whether A or B is true. I know at least one of them is true, possibly both. But what I do know is that, okay, A, well, alpha leads me to gamma, and beta leads me to gamma. So no matter which one is it the true one, both formulas guarantee a third one that is common to both branches. So that formula has to be true. Think of it kind of like this. I go into a split on the road. One split is alpha, the other is beta. They both coincide in gamma. The illusion of free choice. So I don't know much about alpha or beta, but I do know about what is common to both. And that is how this rule works. The rules of biconditional introduction and elimination are very simple. Basically, we are going to break down our biconditionals into the other formulas, and then we'll use those formulas as the rules, as the normal rules. If we have that A implies B and B implies B, A implies B and B implies A, then they're equivalent. Die, monster, you don't belong in this world. About was slain. If we have that either A and B or not A and not B, that is also equivalent to biconditional. And the other way around. If we see or we spot a biconditional, then we can break it down into two conditionals or a disjunction of two conjunctions. As you can see, the elimination and the introduction rules are mirrors of each other, which we call that dual or equivalent rules. The introduction of constant falsehood or contradiction is likewise very simple. It's basically the same as with three proofs. If we have a formula and its negation, that is a contradiction. That is impossible. So we introduce this symbol. And really, the only use of this symbol is Kinda this one. Yeah, it's for the next three rules. If we have a contradiction, then we can just invent any formula that we want. That is a very weird rule, and it's not as useful as it seems. One of the things that I spot a lot with my students is that, okay, they say, oh, well, if I have a contradiction, then I can just invent any formula. I can just add any formula I want. So that means that in all proofs, I should build a contradiction, and that means I will reach the conclusion and win. And I mean, that is valid, except for the fact that most proofs will not have a contradiction in them. But they're so blinded by the apparent simpleness of this rule that they go, oh, well, I'll just find a contradiction in any and all proofs. That way I can just skip on the homework and not spend enough time and doing the homework. And I mean, I appreciate the enlightened laziness. If that were the case, yes, go ahead. But it is very rare that you will find a contradiction in the main proof of most rules. What is likely going to happen, though, is that you will find contradictions inside the subproofs. And that's where the rules for negation introduction and negation elimination come in. If I start a subproof with any formula and I reach a contradiction, that means that the formula will imply a contradiction. Basically, alpha will imply contradiction. So, and because in this logic, this is a bivalent logic, if something will imply contradiction, then it cannot be true, which means that its negation must be true. And the mirror case applies for the negation elimination. If I start a soft proof with a negated formula, very important that it starts negated, and I reach a contradiction in the soft proof, then that means that the formula with a negation implies falsehood or constant falsehood, and that means that the formula without the negation has to be the case. Now that we have a full set of rules, let's do a couple of exercises that are actually interesting. Okay, this is justified by being a premise. This is justified by being a premise. This is just our signal for the conclusion. And okay, I only have two rules. I only have two formulas. Both of the formulas are conditionals, and I don't have anything. Damn parents! It's fine. As always, remember there's a VODs. And if there's any doubts, feel free to ask. So I have two formulas. I'll put this to the side. And there's not much I can do with them because they're both conditionals, and I don't have like the antecedent. I don't have Q or P, so oh well. What I do know is that if I look at the conclusion is also a conditional. So I will have to use the rule of conditional introduction at one point. Okay, so in 3, I open a subproof. I do that by tabbing and adding this vertical line. So I will justify this by hypothesis. And I started my subproof with the antecedent of the conclusion, because I need to go over this again. I want to use this rule, conditional introduction. So if I want a formula of this type, I want to assume the first formula when I open my subproof, and I will end my subproof when I reach the other formula, the consequent, which is not P. Okay, but there's not much else I can do. I need to reach not P, so what will I do? I need to introduce a negation. That means I have to open another subproof. A subproof in which I will start with P. With P, in this subproof, I have the antecedent of 2. So I can extract Q by elimination of the conditional of 2 by the antecedent that is on 4. Because I have Q, which is the antecedent of 1, I can extract S by the same rule, conditional elimination or modus ponens, of the formula at 1 with antecedent that is at 5. In 7, I have a contradiction. Rupert, can you spot the contradiction? Where do I have a formula and its negation? Okay, maybe Rupert's parents are not letting them log in. So the contradiction comes from 3. Whoops. Font change. And I need my monospace font. I will introduce a contradiction by the formula which is at 6 and its negation which is at 3. And that means I can step outside this first subproof and conclude that not P, because I will introduce a negation based on the subproof that started at 4 and went all over to 7. And thankfully, this lets me arrive at the conclusion because I have a subproof that started at 3 and ended at 8, in which I have the first rule, the first formula that appears on the subproof being not S, and the last formula that appeared on the subproof being not P. And that's it. That is a more interesting proof. Or rather, a more interesting exercise on how to do a proof. It is a bit difficult to explain how to do this to people who have never done so, because I have done this kind of exercises for the last 16 years. So my brain just kind of does them on automatic. In fact, that is the whole point. These are algorithms. I have a strategy that applies these methods without thinking. At one point, I went to something called the Logic Olympics, basically super nerd camp for super nerds. And you just do dozens of these exercises in minutes. It gets to be really mindless. Again, that is the goal. The goal is to be able to produce proofs without any human capacity, ingenuity, or creativity. The point is to compute, to just calculate based on a set of given unambiguous rules, and that's it. Let's look at another exercise which might be interesting. Formatting woes. Let me move this over here. This is justified by being a premise. This is also a premise. Now, I want to reach Q or T. That is a disjunction, so I will use the rule disjunction introduction. That means I need either Q or T. In the proof so far, only Q shows up. So I will likely need to find Q somehow. I only have a disjunction and an atomic formula, a propositional letter. So not a lot I can do. Since I have a disjunction, I will have to use disjunction elimination. So I will open two subproofs. The first one that starts with the first formula of the disjunction. I will justify this by hypothesis. And immediately at 4, I have a contradiction. I have P in 2 and not P in 3. So I will introduce contradiction. The formulas are 2 and 3. And I will extract whatever formula I want, because whatever. And the formula I want is Q, because once I have Q, I can have Q or T. So I will use this by elimination of the contradiction which is at 4. Here I have to close this subproof. So in 6, I open the other side of the disjunction, which is Q. I justify this by hypothesis. And guess what? Just like in this exercise, I have Q. Where are we gonna get to? Q. Well, I'm done. From Q, I have reached Q. So I close this other subproof, and then in 7, I will conclude outside the subproofs that Q. Why? Because of elimination of the disjunction. Which disjunction? The one at 1, with the first subproof being 3 to 5, and the second subproof being 6 to 6. And then in 8, I will finally have Q or T by the rule of introduction of the disjunction of 7. And that's it. Another one. Okay, time for squats. Let me stretch first. Okay, this can be like our small break. It's always good to take a little time off, let the brain rest, breathe deep. Also, I hope that you'll join me with my 10 squats. Remember to stretch first, especially those inner bands if you've been sitting down. And here we go. Squat deep. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, hopefully with some slightly more oxygenated brains, we'll deal with the next proof. Wait, I should copy without formatting. There we go. Okay, so I only have one formula, which again, I justify by being a premise. And I have to reach that thing. Okay. Well, I know it's a disjunction, so I have to use disjunction introduction. The only trick about this one is that I have to do it by parts. So in 2, I just do R or whatever by the rule of introduction of disjunction at 1. And then I do the conclusion by the rule of introduction of disjunction at 2. And that's it. The purpose of this exercise is to remind people that the rules apply not to propositional letters, but to any well-formed formula. Since this is a well-formed formula, that means I can use this as a formula to add anything through disjunction. Another one. Okay, let me put this in another page because it's gonna be a big one. So this is justified by being a premise. So we have two formulas that are conjunctions. So might as well extract all the information we want. So we have not P because of elimination of conjunction at 2. We have R because of elimination of disjunction at 2. We have not Q because of elimination of conjunction at 3. And we have S because of elimination of conjunction at 3. In fact, S is not gonna help us at all. So I'll just erase that. How I know that S was not gonna help us at all? Because check the conclusion. The conclusion is not R. S does not show up in any other part of the formula, so we don't really need S. The argument, my bad, not the formula. S only appears on this part of the argument. So we only have one left to analyze. So one is a disjunction that has 3 elements in it. So time to open the subproofs. We open our first subproof with P. We justify by hypothesis. And we want to get R from this subproof. Wait, in fact, no, I'm being silly. What am I even thinking? I already have R. Here it's R. That's the only thing I needed. See, all the shit I talking about earlier, and I completely missed the troll of this exercise. I effectively trolled myself. So I just have R. I just have R from 2, and that's all I need, really. So elimination 2. And I want not R. So if I want to add a negation, then I start a subproof. I want to add a negation to this, so I start a subproof with not R. Hey, you guys got that's a contradiction. Let me copy my contradiction symbol from over here. This is justified by hypothesis. This is justified by introduction of contradiction of 4 and 5. And at 7, I have not R by the rule of introduction of negation that starts with 5 and went all the way to 6. That's it. Yeah, so the only piece of information that was relevant in this argument was this. And this is basically a small proof that, well, not really, more of a first step or an insight into the idea that let me get the alpha symbol. Not formula is equivalent to formula. Now we have 12 rules, but it will kind of suck that anytime I want a double negation, I had to do this entire step over and over again. Look, I already did it once. I have already shown that a formula, I can get the double negation of a formula. So what if I want to add a new rule to my system? Well, that is valid. If I can prove this, if I can prove a biconditional of two general formula or a formula schema like this, then I can add this to my rule system. So let's prove the double negation to save us a lot of headaches. So I want this to be my conclusion, but I have no premises. Well, shit. If I have no premises, then what do? I want a biconditional. So that means I want a conjunction of two conditionals. Okay, so I'll just build two conditionals. I'll build the conditional goes from the first hypothesis. And I want to get to alpha. Okay, well, if I want a formula without a negation, I will just use negation elimination. So in 3, I have a contradiction. So I have introduction of the contradiction of 1 and 2, which means that in 4 I have alpha by elimination of the negation that goes from 2 to 3. And that's it. I have my first soft proof done. Now I have to prove the other way around. I have to prove that if alpha, then no. But I just did that a while ago, so I'll just copy. We do a little laziness. I just literally copy and paste the proof, and I will change the relevant elements. I mean, if you have all those symbols lying around, the recycling is only responsible. Yep! So this is not 7, this is 8. 1, 2, 3, 4, 5, 6, 7, 8, okay. And the introduction of the contradiction is between 4 and 5. No, it is between 5 and 6. And this I get by introduction of the negation of 6 to 7. Oh no, 6, 7! And then I close the seconds of proof. Oh wait, I majorly fucked up. But it's fine because it's computers and I can just quickly fix my errors. Instead of doing this, I'll just get that not alpha. I need implication. Where's implication? Thank you, implication. That none of alpha implies alpha by introduction of the conditional of the soft proof that started at 1 and ended in 4. And then I have to add another one. But it's fine. And then the contradiction is between 6 and 7. Cursed meme, awful. And then this is the subproof that started at 7 and ended at 8, which means that in 10 I have that alpha implies not alpha. And finally, in 11, I have two formulas, which means I can put them together in a conjunction. Wait, I forgot to justify this. So this is the introduction of the conditional that the subproof started at 6 and ended all the way at 9. Now that is funny. 6, 9. And this is the introduction of the conjunction that started not started. The introduction of the conjunction of two formulas, one which is at 5 and the other one which is at 10. And then finally, I get my conclusion, which is this one. Not alpha if and only if alpha by introduction of biconditional that is at 11. Now, this may look silly, and this may look like a lot of useless technical work for something that may appear intuitive. But that is because this is baby stuff. This is the beginner stuff. This whole experience provides a familiar and approachable way to do mathematical proofs. This is a mathematical proof with no premises, which means that this formula is a theorem of my system, in this case, propositional logic. This is an exercise to get us familiarized with how mathematical proofs work at an intermediate level. By intermediate, I mean college entry level. A lot of the proofs that most humans will do, unless they are math majors, can be done through a method very similar to this one. It is very time consuming, but before people get used to like real mathematical proofs at a college or postgrad level, this is good enough. This is a really good way to get into the idea of what real mathematics are like. Real mathematics are not about crunching numbers. Real mathematics are about exploring the structural relationships within systems. And in this system, the structure that a formula is equivalent to saying not that formula, or it is false that formula, that is a valid and proven structural relationship between these formulas. And there are systems in which this is not the case. Not all mappings or structures or frameworks of mathematics work in such a way in that this is true. But this, for example, is true in arithmetic. Instead, just as in arithmetic, we don't have negation, we have minus. Minus 1, okay. 1 is equal to minus 1. So I mean, this is a Boolean algebra, this is arithmetic, they are not the same. but it's an example of a type of structural relationship that is interesting for mathematicians to prove. Now, the other thing, more from the logic side of things, is that what if instead of screaming and pissing and shitting at each other on Twitter, what if debates and discussions could be had in this kind of harmonious manner? What if instead of screaming at each other and pretending to misunderstand any ambiguity and try to gotcha and pound and just make a spectacle out of arguing, which is engaging in heuristics, what if we had like a proper set of rules of what is a valid process or a valid continuation in an argument or dispute? The fantasy of that will be like, okay, we have our set of rules for debates. We're going to see if something follows from what this person is saying. And if this person can get to the conclusion by using the correct rules, then we all agree that that is a valid argument. And if that person can also furthermore prove that their premises are true in a scientific, material way, then we all should change our minds. We should change our beliefs to this new evidence, to this new argument. And that's it. No more bickering, no more screaming, no more death threats, no more whatever. We will all rationally change our minds according to the new valid argument. Well, that is a fantasy. And the reason why it's a fantasy, it's not just because neither human minds nor the real world functions in this highly abstract mathematical way. Turns out that even mathematically speaking, it doesn't work like that. In propositional logic, in the system we're using so far, we can prove anything that is true, and anything that is true can be proven. If we prove it, it's true. If it's true, we can prove it. In propositional logic, it works. It, unlike Todd Howard's games, it just works. It really does work. The problem is that the expressive power of propositional logic is very, very small. It's a baby system for babies. We cannot talk about real mathematics in this kind of system. And in any system that can talk about real mathematics, turns out that there are things that are true, but we can never prove. Dun dun dun. Yeah, and that is the result, the magnificent result of someone called Kurt Gödel. Building blocks to train change of argument and this type of thinking, right? Yep. So it's not that this method of reasoning is wrong. It's that it is either too simple to do anything relevant, or once it gets complex, it becomes incomplete. And yeah, so that is why the dream of just feeding well-formed problems into a machine and having the machine crank out the results based on perfect rules, not only it doesn't work, it will never work, and we have proven forever that it will never work. So I ask you, chat, if this is one of the most important and mind-boggling results of mathematics in the early 20th century, if we have this wonderful theorem about not just one system of mathematics, but all systems of mathematics, if we have this wonderful proof that shows that human ingenuity and creativity and so on will always be needed to do interesting mathematics, why the shit do the fraudsters and scamsters and conmen of the world promise us that so-called AI will replace coders? It's false. It's demonstrably false. We know it's false. It's a blatant lie, and it drives me nuts. Yeah. I'm just talking about pure computer stuff, pure math stuff. Ugh. But anyways, venting done. Let's go back to the wonderful world of syntactic proofs. So now that we have this, now that we have proven this theorem, the theorem of double negation, we can introduce it as one of our rules. We can just let me see if I have it already made. I do. I'm seeing how they've done a lot to ensure people misunderstand and straight up have to access the information. Yes, which is part of why I consider it my political duty to spread information. Information wants to be free. Okay, so we can now introduce this as a rule, as the 13th rule of our system. Basically, it says if we have any formula whatsoever, we can conclude, or we can affirm later in the proof by dn, which is double negation of n. And because we have proven a B conditional, so it goes both ways, it's an equivalence rule, which means that it also goes the other way around. If we have a double negation, whoops, I forgot how the alphabet works. If we have a double negation, then we can take away the negation in any further step of the proof. Now let's do a proof in which we use our fancy new rule. Okay, conclusion, go all the way here. And we have this because of premise. And then at 4, we're going to use our brand new rule and affirm that P because of double negation of 3. And then we can start building the conclusion. We at 5 can have not Q and P because of introduction of the conjunction of 2 and 4. At 6, we take the formula at 5, put it in parentheses and say and R because of the introduction of conjunction of 5 and 1. And finally, in 7, we reach the conclusion because we have this formula and we can add whatever we want by introduction of disjunction of 6. See? We have proven a theorem, and now that we have proven the theorem, we can use it to make more mathematics. And this provides, yes, so far this is pure programming, but this also provides an insight into how mathematics has advanced since the 19th century. Once we prove a theorem, we can use that theorem to do more mathematics. And with that more mathematics, we prove more theorems. And with those theorems, we prove further theorems, and so on, so on, so on. This, of course, is a toy example. But in a way, that is, yeah, that's a bit of how mathematics advances. Once a mathematician proves a theorem under a constraint, whether it is hyperbolic geometry or arithmetic or linear algebra or whatever, you can use a theorem to prove more things. So, how are you feeling, chat? I think there should be not just web pages, there has to be a game. Natural deduction game. There has to be games to do this. I'm looking for stuff. Mm-hmm. Okay, how about this? I'll go to recommend the Professor Layton and Answers Logic Puzzles. I have played the 3 ones for the DS. They're good. I like them, but not all of them are purely deductive logic puzzles. Some of them involve spatial manipulation or puns or language games, which is fine. I'm not saying they're bad because of that. I'm just saying that in a purely for purely deductive puzzles, I'm sure there were Flash games about this shit. I just look. I look for good stuff, and I think that should be the homework for today. Just a bunch of natural deductions. And those who don't want to use a game or whatever, I guess I'll also, your recommendations for the audience is great. Yeah, so okay, that's a good point to cover 5 minutes before we finish the stream. Just like the homework, the one about the night and day puzzle with the answer being, are you a truth teller if and only if the road to the capital is to the left being the answer? Mathematical logic will not solve all the puzzles for you, but it will help tremendously for a bunch of puzzles, or rather, by helping you think in such a way, in an algorithmic, mechanical way. Yeah, that will help a lot with solving the puzzles. There is a specific game developer that well, I mean, it's basically, a lot of the games is basically formal logic, which is Sactronics. Yeah, this Twitch series, this stream series about mathematical logic will help you get into Sactronic games. That is the case. I can guarantee that, because Sac is an engineer, a mathematician. A lot of the games are about logic and programming. For example, Engineer of the People. Let me give everyone the link. You're going to need a Flash emulator. I recommend Ruffle. But that game is literally what we saw in the semantic area of the course. Yeah, it is logic gates with positive, negative, positive circuits. Yeah, I like that flag too. So yeah, even if you don't want to become a mathematician, I think that so much of the world right now depends on the byproducts of the people who made this thing, this project of trying to solve mathematics once and for all. Turns out that you cannot solve mathematics once and for all. And curiously, they use mathematics to prove that you cannot solve mathematics once and for all. But even if you don't want to become a mathematician or a computer scientist, these systems, once you learn to see them, once you learn to identify them, you start seeing that so much of our society is built around the tools of mathematical logic. Not in the way these people wanted, but still in a substantially undeniable way. Learning mathematical logic and learning natural deduction or syntactic deduction will not help you convince people, but it will help you tremendously to not be convinced by mere appearances. Once you do a bunch of these exercises, and I mean a bunch, like 20 for this week is what I will suggest, your brain will change and your attitude towards arguments will change. And you will become simultaneously a lot more open, but a lot more demanding. It's like, okay, you have an argument, you want to prove something, show it to me. Guide me step by step from what you believe, aka your premises, to your stated conclusion. I may not necessarily agree with you, but if you can provide a reasonable chain of steps from your premises to your conclusion, then at least I will understand you a lot better. attaining that discipline rigor. Yes, that is the goal. That discipline and mental rigor that mathematics itself will not give you, but you can use mathematics to practice it. And that is my dream for this series. Anyways, I will try. I have literally hundreds of exercises like this. I will post an image with, or a series of images rather, with at least 10 or 20. 10 or 20. Fuck it. Let's be humble. 10 exercises for people to do, and I will also post the rules. And remember that we have our 13th rule, which is the double negation, exclusive for the people who watch the stream. I will post all of this in a bit, and if I can find a good game about natural deduction, I will post it as well. Okay, we're almost at the 2-hour mark. This was Samuel, your friendly internet uncle that wants to help you get into philosophy, helping you get into mathematical logic, syntactic deduction, mathematized arguments, the good shit. Have a good week, everyone. I'll see you all later.